So, I had this idea since some time, how to connect an antenna of your choice to a magnetron. And I know that this system isn't perfect, and it's probably an impedance mismatch mayhem, but it worked, and it can be interesting for future experimentations, or connecting a coax cable to a magnetron and have its output power somewhere. Probably if you want a directional magnetron, you can use simply a antenna with a horn. This works very well, and you use the original antenna of the magnetron. And probably if you want to connect a coax cable to a magnetron, you'll need a waveguide with the original antenna and another antenna and bandpass filters with tuning rods, etc. And you have to connect the coax cable to the other antenna, and I don't know, but I'm not much into waveguides. It's a complex subject, so I don't know, I did like this. So, what's the setup here for supplying power to the magnetron? Okay, these are the guts of a microwave oven, but there are some differences and adaptations. Okay, first of all, this setup is low power. In fact, instead of supplying 1 kilowatt of power to the magnetron and having like 800 watts of microwaves, I'm supplying it with just 40 watts or kind. In fact, this hack here wasn't possible with a power that high, because it will probably catch fire, make arcs explode, I don't know. So I reduced the power also for this reason, and to be safe. And the differences are that, first of all, I'm using a separate transformer for the filament of the magnetron. I wound this transformer myself. It's well insulated for the 6 kilovolts of the voltage doubler, and the filament is driven instead at full power at like 3.3 volts, 10 amps. And the power is reduced through the MOT here. The MOT has, in series with its primary, some ballasts to adjust the power with switches, and also a variac, but it's less important. And I adjust the power watching this multimeter here, and when I reach 10 milliamperes in series on the carcass of the magnetron, it means that 10 milliamperes times the 4 kilovolts of the supply voltage of a magnetron means like 40 watts, and I adjust the power this way. And to show the operation, I have some toys here, let's call them toys, and these are a neon bulb, and this neon bulb has the leads that are 3 centimeters in length to make the quarter lambda of the 2.4 gigahertz of the magnetron and make a dipole and receive much better. Same thing for this 12 volts light bulb here, filament light bulb. And also there is this flicker bulb, hot glued to a stick, plastic stick, and a classic, the magnificent CFL. So this is stage 1, and I recorded this clip beforehand, before putting on the Yagi antenna, and stage 1 is basically just a dipole antenna that you can see here, this antenna, made with 2 pieces of copper wire, and this dipole antenna is connected to the magnetron through a coaxial cable. This cable is an RG58 classic radio amateurs cable, and according to online data, it's good up to frequencies of like 5 gigahertz. Yes, it's extremely lossy at those frequencies, also these frequencies, but it's just a piece of like 7 centimeters. Anyways, as you can see, this cable is bent upwards. Why? Because first of all, the output of the magnetron is almost certainly unbalanced as a source, while a classic dipole antenna like this is instead balanced. So obviously you need a balloon apparently on the system, and to make a balloon you can try with ferrites, but I tried the ferrites and obviously the frequencies were so high that the ferrites had no effect at all. Instead I tried to bend the cable a bit and provide a bit of inductance along the cable to simulate a balloon, and in fact this had a decent effect, because initially the negative side of the antenna, the cold side here, this one, the G&D, let's say, of the antenna, didn't have almost any effect on gas tubes, light bulbs, etc. Instead, making a bit of balloon, it increased the effect on the cold side of the antenna, and it apparently works a bit. And this is the structure that I made to connect an external antenna to the output of the Magnetron. The idea was to turn the original antenna into a coaxial cable and void its effect. In fact, you see this coaxial structure here made with a cylinder of iron soldered that is kept pressed on the gasket of the Magnetron, and it's pressed with this spring and soldered joint here, making a gentle force on the gasket and making as many contacts as possible on the carcass of the Magnetron to avoid leaking, etc. You also see this mesh of soldered copper wires here. This mesh was needed because when I tried just the coaxial structure, it still leaked a lot of radio waves from the original antenna. With this mesh, it doesn't anymore. Anyways, to connect the center point of the coaxial cable to the contact of the Magnetron, I used the original cap of the Magnetron antenna that is not present anymore. As you can see, there's the exhaust tube for the vacuum and not the cap. The cap has been cut, you can see here, and it's just a ring that is slid on the original antenna of the Magnetron and soldered to the center of the coaxial cable. Initially, I tried with a bigger structure for the coaxial system with an higher tube, but this didn't work at all, especially because this wall structure was too long, reaching and going past 3 centimeters, the quarter lambda of the 2.4 gigahertz, and this was bad because a lot of radio waves were leaking all around. In fact, this structure now is smaller than 3 centimeters in every shape it is, and it was fairly hard to make. In fact, this thing came up to be like 25 millimeters maximum, but still it's not perfect. In fact, there are better ways to do these things, but I like it this way. Okay, let's try this thing. Filament on, variac on, and let's reach 10 milliamperes of consumption on the Magnetron. That will be like 40 watts. I have here this filament light bulb, 12 volts filament light bulb, and with the leads of 3 centimeters of length, and it turns on already at this distance from the dipole, as you can see. Already here, getting far from the axis, nope, and also the polarization, if it's not matched, it doesn't do almost anything. Vertical with horizontal, horizontal with horizontal, and also the rest of the Magnetron doesn't do anything anymore, or almost, just on the dipole. And all around, because it's not directional, around the dipole. And yeah, okay, now let's blow completely this light bulb, like this. Let's touch. Ooh. And it's blown. Nope. Oh, come on. Nothing. It's sparking also on the negative edge, negative arm of the dipole, but not turning on anymore. Ooh! When I do this, there's a terrible impedance mismatch. Oh, come on. Nothing. Okay, now let's see with some gas tubes. Flicker bulb. Need already gloves at this distance. That's fairly powerful. Ooh! 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 Oh, okay. And not on the sides, because the dipole transmits around it, perpendicular to it. Not on the sides. Just perpendicular. Ooh! Ooh! Yeah. Especially more like this, horizontal with horizontal. Maybe the leads inside do as antenna. Anyways, flicker bulb. Obviously. Okay. Okay, now let's try stage 2. And stage 2 is with a Wi-Fi antenna from a laptop. I don't know if you have dismantled a laptop with Wi-Fi, but they have this kind of antenna or similar. And the model is this. With its cable, there are two. There are slots, inductances, I don't know. This is the connection. And I don't know if it works with a ground plane here or not. Anyways, there are also the small micro connectors. And it's connected through a long cable to the magnetron with the same tapping system. Okay, let's try. Filament on, variac on, and let's reach 10 milliamperes of consumption. Ooh, danger zone. 10 milliamperes. Flicker bulb. It doesn't have any range at all. I don't know why. And it's not about the direction. Okay, neon bulb. Okay, it's vertical with vertical, horizontal with horizontal. We got the polarization, but nothing major. Okay, let's turn off this monstrosity. And the fun fact is that the cable gets warm. It's too long, obviously. Okay, I'm gonna show you a thing. You don't see anything but here's the flicker bulb. You see those branches? I can see them with the naked eye. There's the camera sync, sadly. You see those branches in the neon? Cool. Okay. And this is stage 3, and stage 3 means Yagi antenna, and this is bought on AliExpress, and it's the 10 decibels PCB Wi-Fi Yagi antenna, and it works fairly well in my opinion. It's very nice. Anyways, I reached almost full efficiency with this antenna. It worked fairly well at the end, but I had to reinforce the center conductor of the antenna with a copper wire and some solder because I feared that it will blow or something, I don't know. Anyways, same hijack of the Magnetron antenna here with some really small connections soldered here. Okay, let's try it. Filament on, variac on. Let's reach 10 milliamperes of consumption on the Magnetron average. That will be 40 watts average with a peak, with an higher peak of power. Okay, let's see. CFL. Oh, come on. And it stays on at like half a meter, even more. Flicker bulb, let's stand, and it stays on at like 80 centimeters. Or kinda. That's nice. And the directivity is not perfect. Oh. And neon bulb. It stays on up to like more than half a meter. And it has double lobes of field, as you can see. "12 volts filament light bulb, and it stays on up to like here at like 60 centimeters, and increasing, getting near, obviously, and vertical with horizontal, nothing or almost nothing, horizontal with horizontal, actor power. And another thing, the heat. I can feel the heat on my hand and the actual directivity of the antenna. That's nice. Oh, my phone is glitching. Let's make it glitch. Okay, I ruined my phone enough. So this is my old setup for a low power magnetron. The supply system is the same. There's still the MOT with its primary in series with some ballasts, in this case 3 ballasts, to reduce the power. The filament winding of the MOT is not used. Instead there is a separate transformer, a smaller transformer for the filament of the magnetron, and the filament is driven at 100% constantly. I wound myself this transformer here. And the magnetron is unmodified. and there is a cantenna, a tin can, a horn, and a tuning rod. And the tuning rod protrudes inside the cantenna, like sticking out like 2 centimeters, and it's adjusted with a pair of nuts here to have the maximum directivity. And apparently the tuning rod improves the directivity vertically, while the horn improves the directivity all around. And there's also a power meter with a full scale of 60 watts. Okay, let's try it. Filament on here, and you can see it glow. You can see the filament glow through the ceramic, because the ceramic is translucent. The filament must make a lot of light, actually. Anyways, and the power on, and we have like 40 watts or slightly more. Okay, CFL light bulb. Kinda more than half a meter of range. Okay, you can feel some heat actually. I don't feel any pain, obviously. Anyways, neon bulb. It's already glowing. Vertical polarization with vertical polarization, and it glows perfectly. And a range of like almost a meter. Vertical polarization with horizontal polarization. Nope. 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 Anyways, 12 volts filament light bulb. Vertical with vertical. And it glows up to like here. And it's more than half of a meter, like 60-70 centimeters of range. Nope. Or almost. Nope. Yes. Nope. Yes. Okay. And I forgot the flicker bulb. Let's try. And it glows up to like kinda like 90 centimeters. It's a bit better than the Yagi antenna actually, but not by much. It's so bright inside the horn, like the CFL. Okay. So, thank you for having watched my video, and as always, if there are updates for this project, you'll find them in the description of the video below. So at this point, goodbye.